Hello and welcome to Team No Ideas Senior Capstone presentation. My name is Emma Hedrick and I've had the pleasure of working alongside Maggie Gross, George Fidel, Emily Rapp, Frankie Gentili, and Marjorie Sal this semester on this project. We were tasked with designing a chemical plant to convert toluene into paraxylene. So to understand some of the analytics of our project this semester, we're going to talk about three main topics today, that being background information, the overview of the process, and economic analysis. So we'll delve into a little bit about the background information. So this semester we worked with Knitlion Chemicals, located right here in State College with their Research and Development Division. They have a facility already built in Houston, Texas currently. So we'll be taking over that plant or that site just to kind of capitalize on the pipelines that will provide hydrogen feed, which is one of our two feeds for our process. We will, being said that it is in on the Gulf Coast, we have taken into account of all the costs analyses that go into that region. Our start date is going to be January 2023. So, like I mentioned earlier, we have two main feeds, hydrogen and toluene. So our main reaction taking place is toluene into mixed xylenes. That being said, there are two side reactions that are going to be taking place, and we had to design our reactor very carefully to increase the selectivity of paraxylene and the conversion of toluene into the mixed xylenes. So that's a little bit about background information. I will be turning it over to Maggie to go over the process overview.
Now that we have discussed the background information regarding the plant's location and some basic chemical properties, we're going to move into an overview of the general process. Okay, so beginning with our block flow diagram, we have two main feed streams. The first is a fresh stream of toluene, which will join in with a recycle stream, as well as a fresh stream of hydrogen gas that enters for our process. These streams will then go through a reactor where our main reaction, as well as the two side reactions we discussed previously, will take place. We have a series of towers then, which will be used to remove impurities before the stream enters the Parex, which will be our final purification step. The Parex is used to purify the p-xylene from the other xylene isomers. So taking a more in-depth look at our process, we'll begin by looking at the two feed streams that go through the heat exchanger and then enter our reactor. The heat exchanger uses a heated stream from the exit of the reactor to warm the inlet stream, which is a utility cost savings for us. From the reactor, the stream enters a flash distillation tower. The flash tower separates on the basis of volatility and removes hydrogen and methane as the lights products before being sent to the distillation tower then. The lights products coming out of the flash are then sent to a hydrogen purification unit to regenerate fresh hydrogen, reducing the amount that we need to purchase for the feed stream. The methane stream is then sent to vapor fuel storage, which will be used for fuel credits. The second phase of our process filters out impurities from the benzene and p-xylene products. So the first distillation tower used was designed to remove benzene, as this is a valuable product that can be sold once we hit that 99.9 purification target that we needed to sell the product. The toluene impurities filtered out in Tower 2 then are recycled back into the process so they can react further and produce more xylenes to be sold. The purified bottom streams from Tower 2 will then be sent to a third tower to remove the TMB. So after the third tower, the stream is almost our mixed xylene products. So although a series of towers do lead to a higher capital cost for our plant, in this case it is justified to have 3 towers due to their different purification goals and their unique design aspects. They deliver different products for our plant, and they deliver different recycle streams as well, which can be used. So the final phase of our design uses a Parex unit, which uses absorption to separate the p-xylenes specifically from the other xylene isomers in the mixture. The p-xylene stream is leaving the Parex at a purity of 99.9, which is a requirement in order for it to be sold. Additionally, the mixed xylene stream also meets the 99.9% purity spec, So this is sold as well. However, it's not as much as the p-xylene product. So we do meet both of our purity specs, and both of these products are valuable and are being sold from our plant.
Throughout this project, there were a number of hold and soft specs that needed to be met and a number of soft specs that could be negotiated. We were able to meet all of the hold specs, which included the four listed on this slide. The first one being the purity of the chemical products that we produced and ended up selling, which included xylene, benzene, and mixed xylene. The second hold spec that we were able to meet was the inlet and outlet reactor temperature, which included a 650 degree Fahrenheit inlet temperature, which came out of the reactor 700 degrees Fahrenheit. The third spec that we met was the selectivity of p-xylene and benzene, in which these selectivities were taken into consideration in order to optimize the amount of product that we were able to recover and sell. The last of the hold specs that we were able to account for was the recovery of key chemicals, which just ensured that we were able to sell as much of the chemicals that we were able to start from.
So now that we've covered the overall process design, we're going to go into a little bit of the actual economics of the plant. So first we looked at all of the costs of our equipment, which was in the IBL, or inside battery limit. So as you can see, the Parex took up the majority of the costs, with our flash distillation and 3 distillation columns coming up next as the most expensive. So in the future, if we wanted to decrease these costs, we would have to do a little more R&D to look into a cheaper, more efficient way to get the same p-xylene separation that we have now with Parex, but for a cheaper cost. We could also look at getting more efficient distillation columns, which could make them smaller and thus cheaper. So overall, the total contracting cost for the IBL was about $41.5 million. So then we added the OBL total contracting cost to these, which consisted of site development, utilities, raw materials and product storage, and environmental costs. The majority of these costs was from the raw materials and product storage. So then to these costs was added the costs that are up on the graph, which included team costs, pre-operational and startup costs, our initial catalyst buying, and our project contingency costs. So these all added up to a $77.3 million total plant cost.
Throughout this project in this chemical plant, the full operating costs that we had to take into account, which included raw materials, utilities cost, fixed cost, and SG&A, which associated for selling the product. The pie chart on this slide shows the operating costs in these four in terms of cents per pound of the product seen, in which raw materials accounts for 86% of the total plant operating costs.
So to build off these operating costs that Georgia just mentioned, we'll take a little bit of a more in-depth look at some of the utility costs. As you can see, the Parex and licensing of the Parex comprises most of these costs, as this can be attributed to the high flow rate that we were given for this project. It was based on 69,000 pounds per hour, which then operating the Parex obviously depends on. The following utility costs for the hot oil, high pressure steam, low pressure steam, and power for the plant can be seen in this pie chart then.
Throughout this chemical plant, we were able to produce and sell 3 chemicals with a high enough purity that included xylene, mixed xylene, and benzene. On this figure, you can see the selling price, the approximate flow rate, and the revenue per year that we were able to make while selling these 3 products. As you can see, xylene comes up at $102 million per year, with revenue followed by benzene at 82.2 and mixed xylene at 23.6. Although the main goal of this project was to produce xylene to sell, you can see that another main product that we're selling, benzene, comes up with a high amount of revenue that we're making, to total up at $208 million a year.
So just going off of that, each year the plant will earn $21 million, and these revenues are mostly from selling, like George had mentioned, the paraxylene and the benzene. You can see a total revenue of $183 million per year. Some of the costs associated with this project were obviously for the fresh raw material, buying toluene and hydrogen. Utility cost, fixed costs, so like paying wages and different operating costs there, and then the selling and administrative costs at the bottom. For the byproduct and fuel credit, this can be attributed to selling mixed xylenes, which is another product that George had mentioned, as well as the fuel credit that we receive for burning some of our other waste streams, namely from the hydrogen purification unit and from the third distillation column. So as you can see, when taking into consideration these costs, the total profit yielded is $21 million per year.
On this slide, you will see the cumulative present worth versus the yield for our chemical plant. Starting at 2019 and going to 2022 is when the chemical plant will be built, in which the first year will account for 30%, next year will account for 20%, and the last one 50% of it being built. Once the startup date is achieved at 2023, we will begin to manufacture our 3 products at a limited amount until 2 years later in 2025. And as you can see in this graph, by 2026, we will earn back our capital cost, and by the end of our 15-year operating period, we will be able to create a cumulative present worth of just over $60 million.
And so we're able to attribute this high after-tax real return to our high selling price. So this was based on the amount of paraxylene that we're able to produce relative to the amount of benzene. And so you can see this is set at 42 cents per pound of product, and this was calculated using a weighted average of the paraxylene and the benzene products. And then the current value of the ATROR is 29%, which is much higher than our desired value of 15%. So normally this 15% figure is standard for investment into a chemical plant. You would expect to get this type of return in order to make your plant seem worthwhile to do. And as you can see, ours is far larger, so this is a good sign for us. But going off of that, the net present worth or net present value is $67 million per year, and our cumulative cash flow is just under $300 million.
As you can see on this slide, on your left is a pie graph for the raw materials cost breakdown, in which there were 4 main raw materials that we had to buy. The first one being toluene, second one hydrogen, and then followed by miscellaneous chemicals and catalyst. As you can see, toluene accounted for 92% of our raw materials cost, mainly due to our 69,000 pounds per hour feed flow that we had to account for. And then the catalyst had to be bought every 3 years, which is why it is a lower percentage of the cost. On your right, you will see the ATROR versus the toluene cost, which will have the biggest effect on our after-tax rate of return, just because our toluene raw material cost is so high. Currently, our raw material cost for toluene is at roughly 26 cents per pound of product made, and as you can see, as you go down to the 27.5 cents per pound of product, it ATROR tends to drip down below our desired value of 15%.
So in this process, one of our biggest losses of product occurs at the hydrogen purification unit. At this unit, the hydrogen and methane are being purged. However, several thousand pounds of benzene, toluene, and p-xylene are also being lost in this stream. This will bring our total loss of product to around 12%, whereas the target is only 3%. So one way to fix this problem would be to add in a flash distillation unit. The purpose of this unit will be to separate out the hydrogen and the methane, but then recycle the useful products back into the process. And they will be going in right before the reactor, so that the toluene has another chance to go through the reactor and react to produce the useful products. So as you can see on this slide, the capital costs of this flash distillation project will be around $3.4 million. And since the only utility being used in this unit is cooling water, the utility costs are very low, only at around $2,000 a year. So this alternate process, as you can see, has the potential to earn around $17.8 million extra a year on top of our revenue from the original process. This is because several thousand more pounds of benzene and p-xylene are being recovered. However, the purity of the p-xylene product drops below the hard specification of 99.9%. This is due mostly to the toluene impurities in the system. So the toluene distillation tower with the new additional flow rate of toluene is not enough to filter out the toluene impurities to bring the purity of the p-xylene within the specifications. So it is not recommended that this alternate process is considered unless several overhauls are made to the toluene distillation tower. So in conclusion, this process, with a discount rate of 12%, has a present worth of $67 million. It will require an initial capital investment of $77 million. As we've discussed before, the after-tax rate of return is 29%, which is greater than the 15% target, and all of the hard specifications are met. So the xylene purities, the benzene purity, and the mass balance is balanced. However, some improvements that we can make to our process at this point, we do have an unexplained pressure increase at one of the units, so we may need to add in a pump and condenser in a later equipment overhaul, so that will increase our capital costs a little bit. We also are not meeting some of our soft specifications, so the hydrogen and toluene ratio entering the reactor is not exactly 2:1. Our WHSV is slightly above the specifications, and as we have discussed before, the product loss is 12%, greater than the 3% targeted. However, in conclusion, due to the high profitability of this plant, we do recommend that Nittany Lion Chemicals proceeds with the construction of this plant. Thank you.